Okay. So today we are going to begin a new chapter. Do you have any doubts from previous chapter? No doubts. Okay, so the next chapter is application of derivatives. Is my screen visible?
Yes, sir.
Okay. So application of derivatives is an important chapter. And in this chapter, we are going to look for the application, the use cases of derivatives, the concept of differentiation that we have discussed earlier. We are also going to learn about some new tools which will understand how these differentiation in particular is related to other topics. Okay, so application of derivative. In various fields of applied mathematics, one has the quest to know the rate at which one variable is changing with respect to change in other variable. Rate of change most of the time primarily means that rate of change of some variable with respect to time, but it can be other variables also. Okay, so let's discuss one use case of speed and acceleration. Whereas, as we know that our displacement is most of the time represented this by this variable x, time by t, and speed, or should I say velocity, by v. So here in velocity, what we see, the instantaneous velocity, we change in displacement with respect to time. And for acceleration, it is represented by a. We see change in velocity with respect to time. Yes. So we can write it as further as v is dx by dt. So it is the second order derivative of x with respect to t. These are some general, very basic understanding. Okay. So let's now solve the first question in which we have to find out the acceleration. It is given that a particle moves in a straight line in such a way that its velocity at any point is given by v square is equals to 2 minus 3x, where x is measured from a fixed point. So it is position. In other words, it is displacement. Okay. So as we know, acceleration is what? dv by dt, right? So let's differentiate this equation both side with respect to time. On differentiating this, 2 comes ahead, v into differentiation of v with respect to time is equals to 2. 2's differentiation with respect to time is 0, minus 3x differentiation is 3 into dx by dt. As we earlier discussed that dx by dt, where x is position or x is displacement, is what? Dx by dt is v, velocity only. So 2v to dv by dt minus 3 into v. V cancels v. Later we can write, and dv by dt is what? Change in velocity with respect to time is acceleration. 2a is equals to minus 3. So acceleration comes out to be minus 3 by 2. This matches our option number B. Is this question clear? Is this question clear, Tanish?
Yes, sir.
Yes. Please keep on responding. Coming to the next concept. Yes, our Answer matches our calculation. So coming to the next question, which is a good level question. If area of circle increases at a rate of 2 centimeters square per second, then find the rate at which the area of inscribed square will increase. So let's first draw a circle. Okay. And there is a square inside this circle. So something like this. Right. So here we have a circle and there is a square which is inscribed in it. So we know as this must be the center. So let's draw the diameter of the circle. So as we the radius of circle is r. This is also r. So the diagonal of square is what? 2r is the diagonal of our square. And we know from our previous understanding of geometry in class 10th that a circle of side A will be having square root of 2 into A as diagonal. So on comparing to square root of 2 to side, square is equals to 2r. This can say 2 by square root 2. Square root 2 into r is side of square. Okay, so this is what? Square root of 2r, square root of 2r, square root of 2r, square root of 2r. Okay, so now what we have to find that area of circle. What is area of circle? If we have r as radius, it is pi r square. This is the area of circle. What will be the area of square? If we have side is square root of 2r, square root of 2r square, which is 2r square. Okay, so we have area of circle and area of square in variable of r, which r is the radius of the circle. Now we have to find out the change, the rate at which area of the inscribed circle will change. And we have given, what is given? The rate of the area of circle is increases at a rate of with respect to second. So it is given with respect of time. So this is given to us. Okay, we may not write unit every time. Okay, so this is given to us. What we have to find the rate at which area of inscribed square will change. Okay, so for finding this, let us, as we have this function, so let's derivate it on both sides on differentiating. 2 into 2 into r into dr by dt. Okay, so 2 into 2 becomes 4r into dr upon dt. So as we have this given equation, so let's differentiate the area of circle also. So dAc by dt becomes pi into 2r into dr by dt. So as dA, this is given to us as 2. So let's write it as 2 pi r into dr by dt. 2 cancels 2. And here from here we can write 1 by pi is equals to r into dr by dt. So as we have to find out this particular equation, r dr by dt's value is 1 by pi. So for r dr by dt value using from this equation, so it will come out as 1 by pi. The answer will become 4 by pi. Is this clear to you? This is the answer. Is this clear?
Yes, sir.
Any doubts? Any doubts? Should I repeat? Tanish, should I repeat?
No, sir.
Okay. So the answer is 4 by pi. Ours is also the same. Let's discuss about increasing functions. So let's first talk about the basics of function. That what is a function? This is the input, and this whole value will give us some output. So if we are discussing about increasing function, so if we will increase the input, and if fx output increases, so that's how in a nutshell we can call it as an increasing function. Otherwise, if we decrease the input and the output of the functions, output of the function increases. Sorry, if we increases the input and if the function decreases, then we can call it as decreasing function, otherwise increasing function. Let us discuss with this example. If a function y is equals to f of x is increasing function, okay, is increasing function, then, sorry, if it will be an increasing function if f of x increases as x increases. So let us say for 2 points, if there are 2 points and one point is greater than other point, so the output on this particular point should be greater than the other point in this domain of function. And that and in other words, we can write it as that the derivative, this, that the derivative of the function is positive. That is why, like, we know that if there is like a curve like this, so if you take tangent of any at any point, so the tangent will be looking like this. So this will have, if we will find out its slope, this will be positive. Okay, because it's going in, it's linearly increasing, and somewhat it is increasing with x. The y is increasing with x. So that's why slope will be also positive, and we can also understand it with that if we find out its tangent, like taking the angle from here and then doing its tangent, so the angle will lie in the first quadrant, and for all trigonometric functions, the angle lying in first quadrant will give us a positive value. So that's why our like slope is positive. So that's why the function will also be increasing. Let me repeat. An increasing function is that function which increases with input. So if let's say there are 2 points, x1 is greater and x2 is less than. So here it should be greater than the f of x1 should be greater than f of x2. F of x2, f of x1. So why this is increasing function in this domain of this function. Is this clear to you?
Yes, sir.
No. Here it will be. So the slope of the function may be 0 or more than 0 in increasing function. There is a particular case of strictly increasing function where the slope must be f of dash x must be greater than 0. It should not be equal to 0. Here we can write it as increasing function. Okay. So let's talk about decreasing function. If we will increase the input and the function's value will be decreasing, then we'll call it as decreasing function, and slope, it's change it. Its derivative is coming out as negative or negative. Okay. A strictly decreasing function when strictly decreasing function when the derivative when the when the derivative of the function must be less than 0, must be, there's no equality sign. There can be a equality in this some point of time. So let's now discuss about the monotonicity of a function. Let f be a differentiable real function defined on an open interval where a and b are excluded and all the points between them are included. So first case, if the derivative is greater than 0 for all x belongs to AB in an open interval, then fx is increasing on AB. So earlier we were also discussing about the same thing, but here we had an equality included about the derivative, and here also an equality is included. For strictly, it is excluded. The condition of equality is excluded. So let's now discuss about the condition of in the condition as we are discussing this. So the slope, the derivative must be greater than zero, and for all x belongs to a, b, then the function will be known as increasing, monotonically increasing. If the function's derivative is less than zero for all x belonging in the domain, then the function is decreasing on that particular domain. And here, remember the strictly there's no equality condition here. There's no equality condition here. Is this clear? Is this clear, Tanish?
Yes, sir.
So properties of monotonic function. If function is continuous on closed interval of AB such that the derivative is less than or equal to zero, then f of dash c is less than zero. For each c belonging in the open interval AB, then function is monotonically or strictly decreasing. We talked about it earlier. If function and if f of x and g of x are monotonically increasing or decreasing on a, b, then g of f, yani the composite function is a monotonically or strictly increasing function. If f of x is strictly or monotonically increasing and g of x is strictly or monotonically is the same thing, is decreasing, then g of x is strictly decreasing on a of b. So this is about these two conditions are about same about composite function. If f of x is strictly increasing function on an interval, then f inverse exists and it is also strictly increasing function. If f of x is strictly increasing function on an interval, then such that it is continuous, then f inverse is continuous on f of a and f of p. So if a function is strictly increasing function in an closed interval, so the function is also and also if it is given that if the function is continuous, then we can write it as the inverse of the function will also be continuous on this particular domain where we are not taking a and b, we are taking f of a and f of b, okay? Because the range and domain interchanges when we inverses some function. Are all these points clear? If not, you can ask.
No doubt, sir.
Okay. Let's discuss about this example. The intervals in which this function f of x is equals to 2x square minus logarithm of modulus of x is increasing in. So we have to find out the domain of x in which the function will be increasing. So let's now first break down the function because it have a logarithm inside. So not x is not equals to 0. So maybe x is less than 0 or maybe x is more than 0. For x is less than 0, the modulus function will break out like this. For x more than 0, the modulus function will break as it is. So let's now discuss about the derivative of the function. For x minus logarithm of 1 minus x, and the derivative of minus x is minus 1 here. For x less than 0, here 4 of x minus 1 by x greater than 0. So this cancels this, and the basically the derivative is coming out as same. So for x is equals to 0, and f of dash of x is let's as we have discussed about, this is the x-axis. Now let's discuss about the sign of f dash of x for all values of x less than 0. Okay, so as we have f of 4x minus 1 by x, is equals to f dash of x. So let's take x is equals to minus 1. We are just checking the sign. Minus 4 plus 1 minus 3. So this will be negative. What will be negative? F, no, sorry, f dash of x is negative here. Let's check for all values of x which are greater than 0. Let's take x is equals to plus 1. 4 minus 1 is equals to 3. Okay, so this will be positive. So now we have to understand one thing, that we had to find out that the where the function is increasing. Okay, so as the slope is positive here, so what we can see here, that when the slope changes, at some point, like if this is the function's curve, if this is the function's curve, and if this is the function's curve, okay, and this is the point where the slope is changing. Here the slope was like negative. Here the slope was positive. Here the slope was positive. Here the slope was negative. Okay. So here we can see the function is going from minus. The function is going from minus, like the derivative of the function is minus to positive. So minus to positive, it becomes in a what was it like? This was a function who was decreasing like this, and then particularly increasing. So this is the increasing function, and this was a decreasing function, right? So as the case is also the same here. So like for all the value of x, it is increasing, right? Are you with me?
Yes, sir.
For all of the value of x, it is increasing. Yes. Are you there?
Yes, sir.
No, it's not the case, because we have to also the interval in which the function is increasing. So is simply what we'll do, as we have the point of inflection, and we also know the function is changing in an increasing way. So we also have to find out its domain for which it is what, like क्या बोलते हैं, function is definable, defined, function is defined. So laptop is freezing. Is my voice audible?
Yes, sir.
Okay, so earlier what we were, इतनी right side over. Where is it? Yes. So earlier what we were finding, that f of dash of x, and for like say increasing function, we were discussing that the f of dash of x, it should be positive. What it is, 4 of x minus 1 by x 0 greater than 0, and it cannot be, we cannot take the equality, because x, for x is equals to 0, the function is not defined. Let's bring the x up. then this, then 4x square minus 1, this. Um, so we have this algebraic identity a square minus a b square is equals to a plus b into a minus b, right? So we can write it as 2x square minus 1 square. So 2x plus 1 into 2x minus 1 greater than 0. So for this, for this, the function will be increasing particularly. Otherwise, earlier we only knew that the function is changing on this particular critical point. We were not sure about the points from minus infinity to 0. So that's why we are checking this particular condition also. So for we have here, as per here, x is equals to half and x is equals to minus of half, minus half plus half. Okay, so and this is what f of dash of x, and it should be positive. So let's check for the value of, as also we cannot take x is equals to 0. So let's take another critical point over here using our earlier observation. So now let us check for the sign of this. Let's take a value, let's take a value minus 1 by 4, which will lie in this period. And for this, our f dash of x will be coming out as 4 into minus 1 by 4 minus into minus into minus 4. 4 into minus 1 by 4 minus into 1 by x will be minus 4. So this will become plus. Sorry, this will not be plus. Let's cancel this. Minus 1 plus 4. This coming out as positive. 4, say plus 1 by 4. Find out 4 into 1 by 4 minus 4. This is 1. This is 1 minus 4. That is negative. Let me recheck. 4 into 1 by 4 minus 1 by x, that will 4. So 1 minus 4, that's negative. And so this needed to be positive only. Are we doing some mistake? 0 plus 1 minus 1. So this won't be including on this also. For x is equals to 1 by 4, 2 into 1 by 4 plus 1 into 2 into 1 by 4 minus 1. It's half plus 3 by 2. It's half minus 1, so minus half. So this is also negative. And for values from here to here, minus 1 by 4 is what? 0.125. No, 0.250 is minus. And yeah, so let's take minus 1 as in this case. For minus 1, so become minus 4 plus 1 negative. So basically it's changing sign like this. So what we can see, so the function is having positive slope and then negative slope in this particular phase. In this, the function is like this and then it is increasing. The function is decreasing, then it is increasing. So the function is increasing in this period. Can you understand how? Actually, the example I put it this example a little before discussing uh, before discussing the tangents and all. But still you must be having some knowledge about straight line. So here what we are seeing that this is first derivative test. Are you aware about this test? Let me first tell you the context. Hmm. Let us say what is an increasing what we already discussed about increasing function. Let's discuss about maximum. let's say this is a parabola, okay, and this is some point C, and let's take another 2 points. Let's take an interval points between A and B. So here, as from the observation only, that there is local maxima, and let us consider this function is also proceeding further and this side. Okay. So from the observation only, we can understand there is a local maxima in A and B, and it is lying in, it is at x is equals to C. Okay, so how we can write it as technically that on the value on the point C, f of C would be greater than for all values of f of x, where x is lying in this period A and B. Where x is lying in this period. So this is the case of local maxima. Okay, and discussing it further. Okay, and let's take a graph which is like this. And the graph is further proceeding. We don't know and we don't care because we are caring about only our period which is given to us, A and B. So from mere observation, from in this period A and B, the lowest point is on point C. Okay. So now we can say that it is a local minima. The function is going through the minimum value locally in this period A and B, where x belongs to A and B, and f of C is less than f for all values of f of x belonging to A and B. We have already written this. So now, do you understand what is local maxima and local minima? Okay, so let's now discuss about first derivative test. Then only you'll be able to completely understand that example. So this is a simple concept of tangents and normal. And in straight line, let me first tell you about straight line. So straight line is a linear function. The function is like this, mx plus c. This is slope. This is any variable for x. And this is intercept on y-axis. So here the slope is known as a tangent also. Okay. And we can also find the slope using dy by dx, or we can take the tangent of theta. Theta is what? The angle between positive x-axis and tangent drawn at point P, at point which we have to find out the slope. Okay, so there are other methods also. Change in basically change in this is in another form that we are taking some period change of in y and then period change of x. So this is about tangent. So for any curve, for curves also, we find out tangent. Let me draw a figure for you better understand. Let us say this is some curve, okay, and we have to discuss the tangent at some point. So what we'll do, we will simply draw a tangent on this point. Mm, Simply draw a tangent, will be passing through this. Okay, so this is a tangent. Now, this is known as tangent. And how exactly we can find out the equation of this tangent? By differentiating. If let's say the function of the curve is this, so the equation of tangent will be found out by differentiating f of x with respect to x. Simple. And what is a normal? Normal is a line which is normal to the tangent at that particular point. At which point, and here as we are discussing about this p, so let's call this as normal. And as these two lines are perpendicular to each other, so let us say its slope is m1, let's say its slope is m2. So if these two lines are perpendicular to each other, so their slope multiple is coming out as -1. So if we have a tangent of some function as dy by dx, this is our tangent. So for normal, our slope would be -1 divided by this. So basically -1 divided by dy by dx. Simple, as simple as that. Is this clear? Is this clear, Rishi? Sorry, Tanish.
Yes, sir.
Yes. So let's move further. We have discussed about this. So equation of tangent at x1, that x1, y1, this is some function y is equals to f of x. This is some point P. So we have drawn its tangent or this on this curve at this particular point. So the equation of tangent would be this is like straight line. So its equation is y into y1 into dy by dx. This is the slope of tangent. Earlier we were also, sorry, I written here equation. This is slope of equation. Okay. This is also slope of normal. Here the equation of normal would be just the slope will be changed. -1 by dy by dx. It will become minus of dx by dy. So if tangent is parallel to x-axis, so the slope is coming out as 0 because if theta is 0, so tan theta would be also tan 0 is also 0. If it is parallel to y-axis, that perpendicular to x-axis, then the normal's equation will be coming out as 0. Otherwise, the slope of the tangent here, slope of the tangent at that point would be tan of 90, which is 1 by 0. That's why we are writing the slope of normal as -1 of 1 by 0. So 0 will go up and its slope of normal will become 0. Is this clear to you? Is this clear?
So,
And if the tangent is equally inclined, the slope is coming out as plus minus 1. So this is about tangents and normal. And this question would be more clear to you after you have understood about first derivative test. And basically from here you can understand that the function is the function is first increasing and then decreasing here. So in this particular period, the function is increasing from minus half to half. Otherwise, the function would be like this. So this is an decreasing part of the function. This is also a decreasing part. That's why we will take the value of x from -1 to plus half, but excluding 0. So if we have to exclude 0, so what we will write x as minus half to 0, excluding 0, combining it further, this is the unification sign. Okay, then going to half, and half is also not included because we had a strictly increasing. We were discussing about the strictly increasing function. So this will be our answer B. Yes, this is also correct. This is also correct. So is everything clear to you, Tanish?
yes, sir.
Any doubts? If any doubts, please ask. No doubts. Then shall we conclude today's class?
Yes, sir.
Okay, thank you.
Yes, sir.
Jay.